if we look at the Taylor's series and the expansion of e to the I theta, we can show using Taylor's that this simplifies to cos theta plus I sine theta. Now this is done quite extensively in your notes and I'm not going to go through that right here, but it's a very useful formula. This is called Euler's formula, that e to the I theta equals cos theta plus I sine theta. And that tends to give us another way of looking at the polar form of a complex number, because if we multiply here both sides by r, we get r e to the I theta equals r cos theta plus I sine theta. Now r, as you know, is the mod of z, and if we multiply r out by both, we get mod z cos theta plus I mod z sine theta. So just by expanding out and using the fact that r equals the mod of z. But if we go back and look at the Cartesian form, mod z cos theta is simply the x value plus I, and mod z sine theta is the y value. So this is a more useful polar form. So if we regard this as being the Cartesian form, this is a more useful polar form, as we're going to see later on. So now we've got Cartesian form of z, and that's x plus I y. And our polar form, which comes from Euler's formula here, is r e to the I theta, where theta is still the argument, that's the angle from the positive real axis, and r is the length. Okay, so that helps also with multiplication, knowing your index rules. So if we've got z1 equals r1 e to the I theta 1, and z2 equals r2 e to the I theta 2, then z1 times z2 is equal to r1 e to the I theta 1 multiplied by r2 e to the I theta 2. We can multiply the coefficients there, r1, r2, e to the I. Now, when you're multiplying like bases, and the bases are e, we add the indexes, I theta 1 plus I theta 2. And I is common to both of those two terms in that power there, so we can write r1, r2, e to the I outside of theta 1 plus theta 2. Likewise, if we are dividing two complex numbers and we divide the mods, r1 divided by r2, and instead of adding the args, it'll be e to the I outside of theta 1 minus theta 2. So using Euler's formula up here, it gives us another way of looking at the polar form, r e to the I, instead of just r theta, it becomes r e to the I theta. When we multiply, it gives us a nice handy little way to be able to come up with an answer here, r1, r2, e to the I theta 1 plus theta 2. And when we divide these two complex numbers, we divide the mods and we subtract the args. The Mois Theorem, if we've got e to the I theta all raised to the power of n, by your index laws, when you raise a power to another power, you times the indexes, so that's e, it's common to put the I first, I n theta. And also we know from Euler's formula above that e to the I theta equals cos theta plus I sine theta. So if we raise this to the nth power and we raise that to the nth power, we've got e to the I theta all raised to the power of n is equal to cos theta plus I sine theta all raised to the power of n. From this line here, we know that this left-hand side we can rewrite to e to the I n theta equals, we'll leave this one as it is, cos theta plus I sine theta will raise the power of n. But this here can be rewritten. E to the I n theta can be written as cos n theta plus I sine n theta is equal to cos theta plus I sine theta, will raise the power of n. This is De Moivre's theorem, that cos theta plus I sine theta will raise the power of n is cos n theta plus I sine n theta. We multiply the args by n to get n theta over there. So this is De Moivre's theorem. We're going to use this to prove some trigonometric identities, and it is a theorem that you need to know.